Increasing concentrations of trace gases, such as carbon dioxide, are likely to substantially warm our climate through a phenomenon called the greenhouse effect. The heat balance of the Earth-atmosphere system is delicately maintained. Radiation arrives from the sun at relatively short wavelengths, which pass through the so-called greenhouse gases comparatively easily. The Earth absorbs some and re-emits infrared radiation at longer wavelengths, which are readily absorbed by the greenhouse gases. Some of this radiation is emitted back toward the Earth, and some goes into space. The more greenhouse gases there are, the more infrared radiation is absorbed in the lower atmosphere. We expect this to cause the temperature near the Earth's surface to warm and the upper atmosphere to cool. Climate simulations shown in this video use a global model that incorporates the atmosphere, ocean, and land. The atmospheric component includes many observed physical processes. The ocean component is more simplified. It stores heat in summer and releases it in winter. It does not simulate ocean currents. The atmospheric model uses a grid of lines 7.5 degrees apart in longitude and 4.5 degrees apart in latitude. It has 9 vertical levels distributed between the surface and approximately 30 kilometers. The model equations are solved at the intersection points of the horizontal and vertical grids. Here we see surface temperature calculated by a control simulation with a present amount of carbon dioxide. These two views together show two sides of the Earth at the same time. As the animation proceeds, note the boundary between cold air, shown in blue, and warm air, shown in red. This is also the boundary between the mid-latitude westerlies and the tropical easterlies. As Northern Hemisphere summer approaches, the seasonal cycle of temperature is evident. The light source on the globe is specified to represent the proper sun inclination angle for the time of year being shown. The sun's meridian on the Earth provides a visual cue for the season of the year. We see the contrast between land and sea as the continents show temperature extremes in both winter and summer. In winter, colder air penetrates further toward the equator over the continental areas than over the oceans. During Northern Hemisphere winter, the large-scale planetary wave structure in the atmosphere is especially evident. These waves are primarily caused by the distribution of continents and mountains. In the mid-latitudes of both hemispheres, notice the eastward-moving shorter waves embedded in the large-scale waves. These are the typical high and low-pressure systems that we experience as part of day-to-day weather. Outbreaks of cold polar air masses over continental regions during winter are associated with the shorter waves. Animation shows the weekly, monthly, and yearly variability of weather and climate in the model. Remember, in interpreting the climate changes you will see in this visualization, they are the results of climate modeling experiments, not a definite prediction of future changes. Carbon dioxide is the most abundant greenhouse gas. As the experiment with increased carbon dioxide progresses in time, we calculate the globally averaged surface temperature and compare it to the control case. Throughout the experiment, note that the average difference becomes more positive, indicating a global warming. The difference reaches a near equilibrium value of about 4 degrees Celsius during the last 5 years. Once again, we use two views of the globe to animate the distribution of the surface temperature difference over the entire planet during the experiment. During the early years, the warmer and cooler regions are roughly equal. As the simulation proceeds, the land masses begin to show more persistent warming. By year 5, the warmer regions predominate over the cooler areas. But not all regions of the globe in the carbon dioxide-enriched environment are warmer all of the time, because a natural climate variability is inherent in the system. Because of this natural variability of the surface temperature, some regions of the globe can be cooler at times. As we approach equilibrium, important features of the impact upon the climate stand out. Warmer areas predominate. The winter hemisphere shows the greatest sensitivity to the warmer climate. The largest warming occurs at high latitudes, where the annual variability of surface temperature is the greatest. By the end of the first year, the distribution of the surface temperature difference shows no trend beyond what we'd expect from pure chance. The same holds true for the soil moisture difference. No special significance should be attached to the changes in surface conditions at this time. As we rotate the analysis into 3 dimensions, note that the blue surfaces are 3-dimensional isosurfaces of -2 degrees Celsius. Likewise, the transparent red isosurfaces represent warming greater than +5.5 degrees Celsius. The signature of the eventual impact upon the climate is readily apparent in the upper atmosphere. Only 1 year into the experiment, the stratosphere, in response to the instantaneous doubling of carbon dioxide in the lower atmosphere, shows a clear, consistent expected pattern of cooling over most of the globe. Near the end of the experiment, the average for December through February shows that the largest warming at the surface occurs in the Arctic. Regions of greater soil moisture, colored green, show up in the mid-latitudes of the northern hemisphere. Drier areas in yellow are found over southern Asia, southern North America, and over Africa and South America. As the analysis rotates into 3 dimensions, the surface warming and stratospheric cooling patterns stand out. Near the North Pole, the greatest surface warming is found just east of Greenland. The winter polar region exhibits the largest warming at the surface because the sea ice boundary has retreated in the warmer climate. In June, July, and August, the largest average difference in surface temperature is again in the winter hemisphere, this time around the South Pole. Some of the wetter regions at the surface have persisted from winter into summer over parts of the northern hemisphere continents, while the drier regions are still evident farther south and in Africa, in South America, and now in Australia. In 3 dimensions, the areas of greatest warming lie in the southern hemisphere. The stratosphere again exhibits a strong, consistent pattern of cooling due to changes in the radiation balance caused by the increased greenhouse gases. Over the next decade, as computer models of climate systems improve and computational capability advances, the scientific community will be able to provide more definite and accurate predictions of climate changes. The United States and other countries around the world are planning and conducting an international scientific effort aimed at improving the estimations of regional climate changes.